Hello everyone, this is Dr. Abdul Pasha, Department of Electrical and Electronics Engineering, Institute of Aeronautical Engineering, Hyderabad. So, we are in the course of Power System Operation and Control. So, here I am going to discuss about a flowchart for economic scheduling process. So, there will be a system procedure to make the economic scheduling. This will be better explained here with considering one of the flowchart. So flowchart for economic scheduling. Here the condition is that transmission losses are neglected. So this is one of the iterative method. Based on these conditions, we will make the economic scheduling of a given power system network. It may be the idle or thermal case. It may be idle or thermal case. So now we will start with the first condition, start, and with the given information, read the functionalities FNN, FNPD and epsilon. So these are the data we should obtain from the constraints, whatever we defined earlier. After that, assume a suitable value of lambda and delta lambda. So where lambda is the Lagrange's coefficient, and we should take it as a delta lambda. By obtaining the value of lambda, you can extend this to delta lambda. Now set the value of n equals to 1. So if you are setting the first iteration with the value 1, then it takes to the condition to these lambda and here. That means solve the equation for Pn, that is lambda minus Fn by Fn cases. Now you need to check if Pn greater than Pn max or not for the number of units cases. If it is yes, then you set a Pn equals to Pn max. If it is no, then you need to check if Pn less than or equals to Pn minimum. If it is happen, then you should set a Pn equals to Pn minimal value. Then if it is not happen, then set n equals to n plus 1. So this process, cyclic process, will take place up to the value of n equals to n plus 1. If not it is happened for this case, then check if all the buses have been accounted, taken into consideration or not. So if it is happened, then yes, calculate the value of delta P as we already seen, that is a summation of Pn minus Pd. So if it is delta P less than epsilon, then we say that it is yes. Then go for appearing on the screen as print generation and calculate cost of the generation case. So by this the process will be ends. If not, this will not take place, then go for is sigma Pn greater than P. This will be extended to lambda equals to lambda plus delta lambda. If it is obeying the condition as yes, then you may write lambda equals to lambda minus delta lambda case. So like that, this flowchart will gives you the suitable results while defining economic scheduling process. This is the case only when transmission loss is neglected. We already discussed the transmission loss coefficients. So which are depends upon the, these are because happens due to larger the distance covered by the transmission line, due to the reactance term, due to the transformer losses, corona happenings. So all these criteria may be reflected as one of the transmission loss coefficients. When you are going to suppose it to neglect these coefficients, then this process is applicable. The similar case we have when the transmission losses are taken into the account or when transmission losses are considered. That we will see in the next case. This is the method of showing only when the transmission losses are neglected. So here coming to this transmission loss coefficients, which are called B coefficients. So what happens with the B coefficients here means, first of all we need to consider a simple power system. Consider a simple power system having NL loads. Let the load currents be IL1, IL2 up to so on IL. So these loads are supplied by NG generators. Let the generator currents be IG1, IG2 up to so on IGNG. This is actually shown in this diagram. That is, we have here generator 1, generator 2 and up to NG generators. These are given with the currents IG1, IG2 up to so on IGNG. All these are the couple of generators connected to a suitable power system network. The network element here is carrying current I suffix k. So these are given to the loads IL1, IL2 and the final extent up to INL. All these are called the load combinations. Meanwhile, the process of execution of the power supply through the line is going to be handled here in the power system network. Now consider a network with the element called by the name K. So an interconnected line in the system carrying the current IK, let the generator 1 alone supplies the entire load current IL, where IL equals to IL1 plus IL2 plus so on up to ILN1. So which is I equals to 1 to NL IL1. So under this condition, let the current in the K element be IKL, I suffix K. So in a similar manner, if each of the NG generators, they are operating alone also supply total load current IL, while the rest of the generators are disconnected the current carried by the entire network. So the element K changes from its value IK1 to IK2 and also IK3 to IKNG for n number. For small n number, this may goes happen. Let the ratio of IKL to IL be DKI, then DK1 equals to IK1 by IL. This is the first condition. And coming to second condition, that is DK2, that is IK2 by IL. So with this so on it may happens up to DK for n number of generators. So if all the generators are connected to the entire power system network simultaneously to supply the same load by the principle of superposition, they may be represented as IK equals to DK1 IG1 plus DK2 IG2 plus so on plus DKNG IG case. So let the individual load currents remains constant, which will be the complex ratio of the total load current IL. So it is assumed that X by R ratio for all the line elements or branches in the network remains same. So the factors DKL will then be real and not be complex in the case. So like that we can consider the certain assumptions for making the flowchart to be simpler. So the individual generator currents may have phase angles. So the generator phase angles for respective generators may be delta 1, delta 2, delta 3, delta 4, so on up to delta NG it may take place. So with respect to a reference axis, the generator currents may be expressed as IG1 is equal to modulus of IG1 cos delta 1 plus IG1 sin delta 1. In terms of cos and sin, we will represent as a complex variable. Similarly, IG2 can be expressed as complex variable IG2 cos delta 2 plus IG2 sin delta. So this may happens in simultaneous cases as a sequence. So finally IgNg equals to IgNg cos delta Ng plus IgNg sin delta Ng. So for simplicity, to derive this relation, we should consider let Ng equals to the value 3. Then Ik becomes dk1 Ig1 plus dk2 Ig2 plus dk3 Ig. So here when you make the square of this quotient, then Ik square equals to dk1 Ig1 cos delta 1 plus dk2 Ig2 cos delta 2 plus dk3 Ig3 cos delta 3 whole square term plus dk1 Ig1 sin delta 1 plus dk2 Ig2 sin delta 2 plus dk3 Ig3 sin delta 3. This is also one of the square. So what happens with this relation means dk1 square Ig1 square plus dk2 square Ig2 square plus dk3 square Ig3 square plus 2 dk1 dk2 Ig1 Ig2 cos delta 1 delta. This will be added to 2 dk2 dk3 Ig2 Ig3 cos delta 2 cos delta. So which will be added to 2 dk3 dk1 Ig3 Ig1 cos delta 3 cos delta 1 plus 2 dk1 dk2 Ig1 Ig2 sin delta 1 sin delta 2 plus 2 dk2 dk3 Ig2 Ig3 sin delta 2 sin delta 3 plus 2 dk3 dk1 Ig3 Ig1 sin delta 3 sin delta 1 and which is equivalent to dk1 square Ig1 square in modulus dk2 square Ig2 square in modulus also and dk3 square Ig3 plus 2 dk1 dk2 Ig1 Ig2 cos delta 1 minus delta 2. So this again added to 2 dk2 value with the dk3 Ig2 Ig3 cos delta 2 minus delta and again it will be added to other parameter 2 dk3 dk1 Ig3 Ig1 cos delta 3 minus delta 1. So but we know that the currents in terms of powers are supplied by the generators. Then they can be represented as Ig1, Ig2, Ig3. So here Ig1 is P1 by root 3 V1 cos phi. P1 by root 3 V1 cos phi. As we know that P equals to root 3 Vi cos phi. So from this relation, if you derive I value, then it becomes P by root 3 V cos phi. So utilizing this condition, for respective generators like 1, 2, 3, P1, P2, P3 will may execute. That is root 3 V1 cos phi 1, root 3 V2 cos phi 2, root 3 V3 cos phi. Like that we may derive I value as P by root 3 V cos phi. So here P1, P2, P3 are the active powers supplied by the generators 1, 2 and finally 3. And the voltage V1, V2 and V3. And the power factors at the generator buses are being cos phi 1, cos phi 2 and finally cos phi 3 respectively. So squaring this term as Ik square dk1 square p1 square by root 3 v1 cos phi 1 whole square plus dk2 square p2 square by root 3 v2 cos phi 2 whole square plus dk3 square p3 square root 3 v3 cos phi 3 whole square. And again it will be added to 2 dk1 dk2 p1 p2 cos delta 1 minus delta 2 by 3 v1 v2 cos phi 1 cos phi 2. So two variables will be joined together here for mentioning Ik value as a square term. So 2 dk2 dk3 p2 p3 cos delta 2 minus delta 3 will be taken place by 3 v2 v3 cos phi 2 phi 3 and it will be again added to 2 dk3 dk1 p3 p1 cos delta 1 3 minus delta 1, which will be the ratio of 3v3 v1 cos phi 3 cos phi 1. Now the power losses in the network will contains or comprising of NB network elements. That means it may be treated as branches, which is about power loss is given by PL equals to sigma k equals to 1 to NB 3 IK square RK. So here Rk is the resistance of the kth element. Rk is the resistance of kth element. Then PL equals to P1 square K equals to 1 to Ng dk1 square Rk by V1 square cos phi 1 square plus P2 square summation K equals to 1 to Ng dk2 square Rk by V2 square cos phi 2 square plus P3 square here K equals to 1 to Ng dk3 square Rk V3 square cos phi 3 whole square plus 2P1 P2 K equals to 1 to Ng dk1 dk2 Rk cos delta 1 minus delta. This will be the ratio term of V1 V2 cos phi 1 cos phi 2. Again it will be added to the quotient 2P2 P3 K equals to 1 to Ng dk2 dk3 Rk cos delta 2 minus delta 3 by V2 V3 cos phi 2 cos phi 3 plus 2P3 P1 K equals to 1 to Ng dk3 dk1 Rk cos delta 3 minus delta 1 by V3 V1 cos phi 3 by cos phi 1. Now you should consider one of the loss coefficients B11 to the B31 case. So these are treated as one of the loss coefficient. So by assuming that loss coefficient as 1 by V1 square cos phi 1 square sigma dk1 square Rk, then it becomes B22 as 1 by V2 square cos phi 2 square sigma dk2 square Rk. And B33 can be represented as 1 by V3 square cos phi 3 square sigma dk3 square Rk. And one more coefficient called that is B12, that is cos delta 1 minus delta 2 summation k equals to 1 to Ng, then it becomes dk1 dk2 Rk. Then this is V1 V2 of cos phi 1 cos phi 2. Now B23 coefficient is cos delta 2 minus delta 3 summation k equals to 1 to Ng dk2 dk3 Rk by V2 V3 cos phi 2 cos phi 3. Now B31 coefficient is cos delta 3 minus delta 1 k equals to 1 to Ng dk3 dk1 Rk by V1 V3 cos phi 3 cos phi 1. So here loss coefficients are represented as P1 square B11 plus P2 square B22 plus P3 square B33. So like that it will be represented. It should be added to 2P1 P2 B12, 2P2 P3 B23, 2P3 P1 B31. All are the sum, they may be taken as single summation case with m equals to 1, m equals to 1. So this may extended up to third case, that is 3 up to 1 2 3 PM BMN PM. This product will give one of the loss coefficient here, power loss coefficient. So in general, the formula of BMN coefficients can be expressed as BMN equals to cos delta m minus delta m by Vm Vn cos phi m into cos phi m, which is the product of summation k dkm dkn or kks. So in the matrix form, whatever we written for loss coefficients or B coefficient, the loss formula is expressed as for n generator system. For n generator system, the P1, P2 up to so on Pn is represented in the matrix as B11, B12, so on up to B1n. Similarly, in the second row, B21, B22, so on up to B2n. And in the final case, when it is extended with the n number, Bn1, Bn2, up to so on Bnn case. All these matrix combination is multiplied with P coefficients. Those are called P1, P2, P3 up to so on Pn consideration. So this is the representation here. All the P1, P2 coefficients multiplied to the B coefficients case, where B coefficients are called transmission loss coefficients. These transmission loss coefficients will derive the condition for economic scheduling of the generator systems in idle and thermal conditions. Now, the following assumptions are made for necessary maintenance of the B coefficients. They are to be treated as constants as a total load and a load sharing between the plants vary. So, these assumptions are all load currents maintains a constant ratio to the total current. Next, voltage magnitudes at all the plants remains constant. Third condition is ratio of reactive to real power, that is power factor. Power factor, that means ratio of reactive to real, that is equals to the power factor at each plant must be constant. Must be constant. Now another assumption is voltage phase angles. Voltage phase angles. It may be V at an angle theta or V at an angle phi. Voltage phase angles at respective plant buses remains fixed or constant. So these are the assumptions must follow for suitable operation of economic scheduling of the power system network for a given period case. So these constraints must be considered with the equivalent to assuming that the plant currents maintains the constant phase angle. So we should treat it as constant phi or constant theta for the respective voltage case, that is V theta or V at an angle phi with respect to the common references. That means since source power factors are assumed to be constant. So as per the assumption 3 we made, that is a ratio of reactive to real power nature, that is power factor at each plant remains constant. So power factor must be constant at each case. There is a simple problem given while making the economic scheduling process optimally, that defines a better application of this condition. That is 3 power plants of total capacity each of 500 megawatts are scheduled for operating to supply a total system load of 350 megawatts. So find the optimal scheduling if plants have incremental cost characteristics, that is DC1 by dP1, DC2 by dP2, DC3 by dP3. First one is 40 plus 0.25 P1, second one is 50 plus 0.3 P2, third one is 20 plus 0.2 P3. Here power demands varies from 30 to 150, second power demand is from 40 to 125, third demand is from 50 to 220. So to solve this type of problem, we should treat economic load scheduling among the power plants with the necessary condition with the Lagrange coefficient dCi by dPgi as a lambda. So for the 3 plants, dC1 by dPg1 equals to dC2 by dPg2, dC3 by dPg3, which is equal to lambda. So given total load as Pg1 plus Pg2 plus Pg3 is 350 megawatts. So when you equate these coefficient, that is first one, second one, third one as 40 plus 50 plus 20 plus is equal to lambda, then dC1 by dPg1 equals to dC2 by dPg3, which is equals to 40 plus 0.25 Pg2, and this is equal to the second expression, And if you simplify this condition, you may obtain one of the Pg2 value, that is about 0.833 Pg1 minus 33.33, or you may get the expression 1.833 Pgi plus Pg2 383.33. And if you simplify these conditions, finally you may obtain one of the Pg3 value, that is 214.73 megawatts. So substituting these values of 1, 2 in the for getting 3, then 43.29 megawatts of power will be developed. So like that we can make the simplest process for economic scheduling of the power system networks. So these are some of the common references whichever I have selected for making the smooth operation of this presentation. So thank you. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.